So today we are going to start lecture 26 on helicopter dynamics, and here I am going to discuss some effects which we did not consider before and which have been raised by some people. That is the effect of gravity on blade flapping. I am Dr. Ranjan Ganguly. Now, in the previous lectures when we derived the equation of motion for a flapping blade, a rigid flapping blade, and so on, we have ignored the effect of gravity on the rotating blade vibration. Now, today we are going to show why this neglect of gravity is reasonable, and I'm going to show it by deriving the equations of motion with gravity included. So let's again consider the force equilibrium equation of a flapping blade, and for simplicity we assume there is no offset hinge, so the hinge is essentially at the hub, and we will include the effect of gravity. So this will keep the equation simple, but it will let us grasp through modeling whether gravity is important or not for the flapping blade. So the first thing we do as usual is to draw the free body diagram of the flapping blade. So this is your blade here, it's rotating, this is the flap angle, and we consider some small mass here at a distance r, and this small element is of length dr, and the mass per unit length of this blade is m. So now on this mass, several forces are going to act. We have already considered this system before, and we included centrifugal force, we included the inertia force, and we also included the aerodynamic force. Now today we are also going to add the gravity force here, and as you know, gravity is going to add downwards, and this is essentially the weight of this particular mass here. So let's write down all these forces. So again, you know from our previous study that the centrifugal force is going to be m rotation speed square into r, and the moment arm is r beta, which means if this is your centrifugal force here, the moment arm is this distance, and that is r beta. Okay, so r into beta, assuming small angle beta, of course. Now similarly, the IF is m r beta double dot in this direction, beta being in this direction, it is opposed to beta, and the arm here is approximately r, once again assuming small angle. Then the aerodynamic force is Fz, that's in the vertical direction, because again it's a rotating blade, and so the lift is going to act primarily vertically. The moment arm is r here, and then finally we have the gravity force acting downward. This is mg. So again, you all know that gravity is mg, and the moment arm is given by small r here. So what I'm going to do is take the moments at the flap hinge as we did before, and so we take all those forces, you multiply that by the moment arm, and we integrate this from 0 to r, and we have dr here. So we already know that IB is integral 0 to r mr square, and using this definition of IB, we can remove some of the integrals and write this equation in a simpler form. So this is our flapping equation in terms of time t. So you have the double dots here. So this becomes IB beta double dot plus rotation square beta. The first term, of course, we obtained before also. This is coming from the aerodynamic force. And this is the new term which has come because of the gravity force we have included today. So now we are going to take a closer look at this gravity force. So this, if we take g out, so g is not going to be a function of r. That's like a constant 9.81 meter per second square. That's gravity. So I can pull it out of the integral, and so I get g into some quantity sb, which is the first moment at the flap hinge, that is mrdr. Okay, so I can define sb as 0 to r mrdr, and you can think of it as blade mass into the distance from the CG. So it's the radial location from the CG. Okay, So we can then write this equation in a more compact form. Let us go from the time coordinate t to the time coordinate psi. So my beta dot becomes beta star, and I get this equation here. Now, the first three terms we have seen before: beta double dot from inertia, beta from centrifugal force, and the AFC coming from the aerodynamic force. Now, this is the gravity term, and we are going to see how strong this term is or how big this term is. Now, you can clearly see this is a static load term, so essentially it is going to have some small impact on beta in a static sense. Whereas the Fz here could be a dynamic term, that means it could involve time itself. Here it could be a function of psi, or in the previous equation it could be a function of time t. So now we are going to look closely at this equation and see the size of this term. So first let us look at SB star. So SB star is RSB by IB, and I can write it in this form, and assuming a uniform mass I can pull m out of these integrals, and I can see that this is 3 by 2. Now let us consider typical numbers for a rotor blade. So the G by rotation speed square into R term, this has this form here. So typical value of G is 9.8 meter per second square, rotation speed is 37.7 radian per second square, and radius is 5 meters for a helicopter blade. So I can get this term to be something like 0.00137. So it's a very small term. It's 1 by 1000 or so. So this term being very small, I can essentially neglect this term. So again, if you think physically, this term is the ratio of the gravity force to the centrifugal force. And what this mathematics is telling you is that the gravity force is very, very small compared to the centrifugal force. So a small value of this ratio means that the rotor behavior is denoted or is primarily governed by centrifugal force. Now, blade weight therefore has a small influence on the flapping dynamics of a helicopter rotor. So let's return to our equation. What we have shown here is that the term coming due to inclusion of gravity effect is very small, and its effect is going to be very small because G is very small compared to rotation speed square R. Now, of course, this could change if your rotation speed was less or if your radius was less. So, if you are dealing with rotors of different sizes, maybe you have a small drone or a quad rotor, you have to do the math differently, but then there the rotation speed may be more, the radius may be less, so this thing may still hold in those cases. So again, this is an interesting thing to keep in mind. Now, for a wind turbine blade this may not work, so you need to keep these things in mind, that all these equations which are being derived are system dependent or configuration dependent to some extent. So now if I were to solve this equation, what this gravity would do is that it would get a small coning angle which would be a constant, and this is typically going to be about zero point 0.1 to zero point 0.2 degree negative. That means it's going to have a small negative impact on the coning or the blade flapping. So that's something to keep in mind. If your flap angle is 6 or 7 degrees, then the effect of gravity would be to lower it by zero point 0.1 degree to zero point 0.2 degree. So if you are very much interested in getting very exact solutions, then you need to include the effect of gravity also. Okay. But in many cases in helicopter dynamics, we neglect gravity because we are interested more in the dynamics of the problem than in the statics of the problem. So we'll end this video here. I will see you in my next lecture.